Okay, hello everyone. Looks like we're live now. So we're going to go through some of the review slides, then we'll look at some of the written problems, then we'll come back to the review slides. I apologize, when I posted the slides on Canvas, I forgot to change the number from 26 to 25. In a normal semester, we would have had a lecture in between here on computational geometry. And we didn't have time for that because of the way the university scheduled the no spring break week, but they did schedule the, personal well-being days or whatever they called them, basically took away a lecture. So not a huge loss for you because we never put the computational geometry on the final. But you can actually look at our YouTube channel, just look at all the videos. If you really want to see the lecture just for your own sake, look back at the previous lectures from previous semesters. There's one in there. Anyway, so the exam, I already posted on Piazza about this. So Friday is our scheduled day from the registrar. 8 a.m. is our scheduled registrar time slot. So we're offering at our scheduled time, which is 8 a.m. And we're also offering it at 1:30 p.m. and 10 p.m. And so like the midterm, there's no need to tell us up front. If any of those slots work for you, then do it then. You don't have to tell us anything. But if those slots don't work for you, we need to hear from you like really soon, like today, on the alternate exam request, which is on Canvas. Let's see. So COVID policies like the midterm, open book, open notes, or basically open lecture notes, lab project. You can use anything we gave you. However, that doesn't mean it's easy to find what you want. So be deciding what you might want quick access to, like, I don't know, each of the different sorts, what their complexity is, what's their worst case, what's their best, what's their average, what is the, oh wait, hold on, I'm thinking sorts. That was before the midterm. Sorts was before the midterm. So we should be looking at graphs, hash tables, etc. We're not going to ask you any specific questions about material from the first half, but there will be some things that you'll need to know, like how to use a vector. We're still going to be using those. How to look at complexity of the things we've done since the midterm. For the written problems, we suggest you use an IDE. Don't try to compile and make up test cases and everything. Just type it in your IDE just so that you can get the auto indenting and everything else looking right. You should have some way handy to think about it though. Either print it out or have it just a sheet of paper and a pencil or a tablet and be able to sketch out diagrams and plan out how to solve the problem without code. Once you know how to solve the problem without code, then learn how to solve it with code. The multiple choice is going to be the same format, 24 questions, 2.5 points each. The only big thing that's changing, and it's not too big, is where you download the starter files for the written problems. So on the midterm, there was a link that said basically click here to download the starter file. Well, we had a half dozen or so people who just couldn't download, and the link said anyone with the link can access this, and we still had people who were posting on Piazza. One person who couldn't get to Piazza was emailing us in a panic. So instead of all that, you just go to the AutoGrader, click on the exams tab, and then there's a little button. It looks kind of like an arrow and a hard drive, and it's next to the timestamp, like 21.04. whatever. So don't click on the timestamp. If you click on the timestamp, it'll tell you to look for the icon to the left of the timestamp. So just click on that. It won't download a tarball. It'll just download the starter file, the .cpp file directly. So you just download that, edit it, upload it to Gradescope. You're not going to submit to the AutoGrader. We're just using the AutoGrader to give you the starter file so that we don't have anybody with broken link trouble, etc. One other thing. For downloading the starter files, remember, A through K is AutoGrader 1, and L through Z is AutoGrader 2. And I put those links in the Piazza post. So what you don't want to do is start the exam, close the exam, go back to Canvas, open up the link, then go back to the exam. Just have the link open ahead of time. The worst you'll have to do is refresh it to make the starter file visible. So the exam itself, we're going to be submitting the multiple choice in the Canvas quiz like usual. Just don't submit until you're done with the written problems, because just like the midterm, the written problem question material will be in Canvas. The only thing that's changing is where the starter file is. We always have people who can't display graphics, and I don't know why, because people who have been able to look at lab quizzes, which sometimes have graphics, fine. It comes to exam day and the graphics, they just get broken links. So the things that we've found that make it better is, oh wait, we're on that slide. Yeah, I was thinking display issues. Because extended time people will have more time, basically when we tell Canvas this is how much time is allowed, we had to give it 4 hours and 20 minutes for how much time is allowed. But if you're not on the extended time list, you will only have 2 hours and 20 minutes, not 4 hours and 20 minutes. So it may tell you when you start that you started late. Well, that's just because you're limited to, if you don't have the extended time, you're limited to the 2 hours and 20 minutes. Just remember, your starting time is one of the 3 posted. So if you've got no SSD, no extended time, you start at 8 a.m., 1:30 p.m., or 10 p.m. I saw someone ask a question about downloading. We will basically make the project visible just a few minutes before the exam starts. So you can't download them like a day early. There's slight information in there, not a lot, but there's some information about, the parameter name, stuff like that. So just download them when you see it. Just basically, I'm planning on making it the project visible and thus the download visible like 5 minutes or so before the exam starts. Okay, when you are writing the coding questions, make sure that if you want a helper function, just write it above the given function. If you need a structure, you can put that outside of the function. You can put it inside of the function. It works either way. There's things in here about lines. These have not changed since the midterm, so we don't really need to go through that too much. There's a line in here that if this was something, and I don't think, I've done the practice or done the real exam problems. I don't remember if I did this or not. I can't remember. But if you ever need to do this, you don't need 4 lines of code to add a structure to say a vector. You can just say, hey, I'm going to push back parentheses, and in parentheses, use curly braces to say, hey, here's the contents of a structure that I want to add to the vector. So this thing has a line count of 3. If you had to declare that, then 2 lines for that. But it gets the adding something to that vector done in 1 line of code. Yes, you could. You could in placeback if we had a constructor. This struct doesn't have a constructor, so I don't know if in placeback works with no constructor. I always use in placeback with a constructor. So that would be, hey, that's something to try before the exam. See if this works if you just change it to in placeback and get rid of the curly braces. Try it out. Okay, the libraries, the coding questions will either tell you this is what you're allowed and don't include anything else, or it'll say, hey, we included everything we can think of and feel free to delete or add. So it'll depend on the question and the semester, etc. So just look at the practice question happens to be one that we said use anything from the STL you want, so we included 20 things. And there will be somewhere in the coding question, there will be a line that says basically, and it's in the practice exam something like, do not modify anything above this line. So that'll tell you what you're allowed to change and not. So just look for that comment that says don't modify anything above this line. And I don't remember the exact wording, but I made the real exam starter files the same comment that's in the practice question starter file. For loop variables, you should be using whatever type makes sense to you. So size t, int, etc. Just we don't make the compiler super pedantic about types on the autograder, although you should be consistent with what we give you. So if we give you a vector of integers, then use integers for the contents of the vector and whatever you do with that contents. There's 2 practice exams posted on Canvas. There's also some extra questions. There's places to submit extra questions on Gradescope. You can do as many or as few of those as you want. I would suggest do at least one DP question, because there's going to be a DP question on the exam. Topics, basically, like I said before, cumulative, but we're focusing on things since the midterm. Let's see. Okay, so that starts the review section. What I'm going to do here is I'm going to change over to, I got the practice exam 1 loaded. Oh, hold on. It was all set to go when I had this all set to go before I started, and then it decided to go mess things up. Okay, so let's go down to this problem. It may not be shared properly for just a second. Okay, so hopefully you can see the practice problem here now. Okay, so this is a dynamic programming problem from a previous exam that we're going to look at together. So the question here says you're given a 2 by n board. The 2 is critical because one of the sizes is fixed, and we have to create a function that will figure out the number of ways to distinctly tile this file. Now we'll get to the distinctly in a minute. What we want to do is look at how do we get to the answer. How do we get from the statement of this problem to the answer? So one of the things, I'm going to make a couple suggestions here. One is that when you have a DP problem, look at the requirements. O of n time, O of n space. So when it says dynamic programming problem and you're allowed O of n space, then you probably are going to need a memo that's size O of n. So that these requirements can give you tips about what the form of your solution is going to end up looking like. Okay, so for this one, I'm just going to go to a blank page here, and let's just look at a few different things. So if I said I want to look at n, the number of tilings, and examples of those. All right, so we're going to use this to work it out. So when n is 1, remember it's 2 by 1, so it's 2 rows, 1 column. So the only way to do it is like that. And remember, I forgot to point out on here, these are the 3 types of pieces you're allowed to use. You're allowed to use a vertical one, and you can put them next to each other. You can do horizontal ones, and you can stack them on top of each other, etc. And then there's a 2 by 2 block. And we didn't do like custom shadings on here, but assume you can tell these apart. Like maybe this one has lines like that, this one has lines like that, and this one has dots on it. So we can tell what's what. We can tell them apart. So if we look at size 1, the only way to do a size 1 is to have 1 vertical tile, and that's it. So there's one way to do that. Hello, buddy. My cat wants attention, of course, while it's lecture time. Come here. You're going to show cat if you're going to want attention. Come here. This is Spencer. He's not big on being held. He's big on being petted on his terms. Okay, you can sit on your own chair and you just hang out. Okay, back to the problem. All right, so if n was 2, well, we could take the vertical one we had and we could add another vertical one next to it. We could not start with a 1 and just put a big square one out, or we could stack 2 of the horizontal ones. So that's 3 ways. Now, when we say I want to do n equals 3, let's map out how we could get there. All right, so what if we started with 1, right? So if I started with this, what I could do is I could take that 1 and add another vertical, I could add 2 more vertical ones next to it, or I could take my vertical 1 and I could put a big square one next to it, or I could take my vertical 1 and put 2 horizontal ones next to it. Now hopefully that's showing on the share properly. Yeah, I think so. Okay, my preview looks all right. Okay, so that's how we could get from 1 to 3. Now how about from 2 to 3? So I could go this way. I could start with 2 vertical ones, and I could add 1 more vertical one, or I could start with my big square one and add 1 vertical one, or I could start with my 2 horizontal ones. Whoops, that's a slight mistake there. Where's my undo button? I could start with my 2 horizontal ones and add 1 vertical one. Don't steal the pen, you doofus. Okay, so that looks like 6 ways, right? But let's go back to that word distinct. When I look at these tilings, remember, these are like, what did I say, these are striped like that. And so it doesn't matter if I put down 1 and then 2, or 2 and then 1, these are the same. So there aren't 6 ways to get this, there's 5. Now, if you got the answer that came out with the 6 instead of the 5, it was worth, I believe, 1 point on the problem. Maybe 2, but it wasn't more than that. And so if your relation that filled in your memo did it with the duplicates, it was like 1 or 2 points at most. All right, so we've got this example. Now, how did we get here? All right, so I could go back by, if I look at the ways to get here, if I do any of these, I have to add a vertical one. So if I pick any of those, I have to pick a vertical one. So basically it's, so the number of ways, so the number of tilings for, let's say, I is equal to the number of tilings for I minus 1, I minus 1, and I have to add a vertical one. So if I start with 1 back, so when I'm working on, let's say, size 3, I could start with size 2 and I have to add a vertical one. So it's that number of tilings. So if there was 3 ways to do the size 2, then there's 3 new ways to get to size 3. Plus the number of tilings for I minus 2. Well, here's where the distinct comes in. If we say times 3 here, we get duplicates. But if we say times 2, we get the distinct. Or unique. I can't remember if the problem says distinct or unique. So that's basically our formula. So now we just have to take this formula and put it into code. Okay, so let's go back to the previous page. All right, so we could say, oh, did I load? I loaded up the answers. I meant to load up the questions file so we could look at this. Okay, well, we're looking at the answers. So I accidentally loaded my answer PDF. I normally load the question PDF. Okay, so I've got actually here on the solution here, I've got, here's a top-down helper and a top-down function. And so this was a way to do this with a top down. And then, no, okay, I thought I had both solutions in the PDF, but now I'm only seeing one of them. Maybe I loaded the wrong one on my tablet, because let me look at the, so if I look at the PDF real quick that I uploaded, it looks like the PDF has both answers in there. So we're looking at the top-down version. And then what we can do is, why don't we write a bottom-up? Since it's not visible on my tablet right now, let's write the bottom-up together. Okay, so if we want to do a bottom-up, let's see, where do I have room? I'll just start right here. And I'll double check. After lecture's over, I'll make sure that the PDF that's on Canvas has both answers in it. Because for some reason I've got a PDF on my tablet that just has one answer. And I was pretty sure I did both. No, it's not there. Not there. Okay, anyway, we'll do the bottom up together. So I need to create a memo. So a vector of int. We could say let's give it a name, like we could just call it memo. And it saves us room if we create it up front. If I put something in parentheses here, it's like doing a resize, but it doesn't take 2 lines to do it. So I need to make things easier on this problem, and when you do any of these problems, you have to figure out, do I need n in there or do I need n plus 1? So this one, if we think about, like, how many tilings are there for size 1? How many tilings are there for size 2? Well, it's easier, I think, if the index corresponds to the number of tilings. So I'm going to make this n plus 1 so that there can be an entry for 0 even if I don't use it. So even if I don't use the entry 0, at least when I'm talking about, like, the number of ways to tile a board of size 3, it's at index 3. And the number of ways to tile a board of size 5 is at index 5. And then index 0, we might use it, we might not use it. Okay, so I've got that. Then since we're going to do a bottom up, we need to put some base cases in here. So I could say, like, memo sub 1 is equal to 1, because we did that example a little while ago. See, so when n is 1, there's one way to do it. When n is 2, there's 3 ways to do it. Okay, so I say memo 1 is equal to 1. Memo sub 2 is equal to 3. We could also, equivalently, we could say memo sub 0 is equal to something, and memo sub 1 is still equal to 1. Okay, so here's a question. How many ways are there to tile a board of size 0? There's one way to do it, and that's to pick nothing. Now, if you look at this and look at our equation, so we said the tilings for size I is equal to tilings of size I minus 1 plus tilings of size I minus 2 times 2. And if we look at this, if I say memo sub 0 equals 1 and memo sub 1 equals 1, then memo sub 2, so memo sub 2, so number of ways to tile size 2 is equal to the number of ways to tile size 1 plus the number of ways to tile size 0 times 2 is equal to, that's 1 plus 1 times 2 is equal to 3, and that's what we got. So either one of these base cases works. So now we need a for loop. Since I've got my n as an integer, I'm going to make my loop an integer. So int I is equal to 2, let's say. Let's say 3. Let's start at 3. Let's go with the original example. So I equals 3, and if we were doing this version, we'd start out at I equals 2. All right, so we start out int I equals 3. I is less than or equal to n, because we've got to get all tilings basically up through and including n, plus plus I, and then we can just say memo sub I is equal to memo sub I minus 1 plus memo sub I minus 2 times 2 and semicolon. And then when we're all done, oops, I'm running out of room here at the bottom of the page, we could just return, we could say memo sub n, or we could also do memo dot back. Either one would work. And then we just need a closing curly brace and we're done. Okay, so that's the tilings problem. So things to take away from this, how to solve DP problems. First, like I said, look at the requirements to get an idea of what you are going to do for the memo. For instance, if we say you're allowed to use size m times n, and we give you input that's m times n, then it sounds like you're going to have a square memo of size either m times n, or it could be m times m plus 1 by n plus 1, depending on how you view the solution. So when you look at the requirements, look at that as a way to think about the memo. And then the other thing you have to do is come up with the relationship. How is this element of the memo related to other elements of the memo? And generally, it's going to have to be related to more than one, at least in the average case. Because if one memo element was just related to one more, then we don't really need the memo. I really just need like the previous variable. So generally, and also if every element, think of it this way, if every element was only dependent upon one, we don't have the exponential explosion that, that DP requires. If every value is based on just one previous one, then we don't need DP really. So for it to be DP, in at least the average case, something in the memo has to be related to at least two other things in the memo. Okay, so then we can generally also, when we give you a DP problem, we will give you a problem that can be solved with bottom up, or it can be solved with top down. And you can go for the solution that makes sense to you. Our line requirements are written with the idea in play that, hey, if you make the top-down solution, it might require a few extra lines because I've got to have the function header. So when I write a helper function, the helper function header counts as a line, and then we can add these all up. So if we don't count curly braces, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops, I counted the int line, so 8, 9. So 9 lines, we allowed 12. 12 was basically the top down plus 3 lines to spare, and then the bottom up took us just 1, 2, 3, 4, 5, 6 lines. So yeah, the top down will take a few more lines, but it'll still fit within the line count. So you can solve these whichever way makes sense to you, and take the time to draw out and understand the problem before you start trying to code it. Having the relationship at how we get there. Okay, it looks like, I'm not sure, I don't seem to be having anyone else answering questions here. I'm gonna send out the bat signal. So that's basically this picture. This is where we started before we got to the code. So if you joined late, you might have missed this page. So I started out with one tiling and said, how do I get to a size of 3? Well, I start with a size of 1, and I get to 3 by either taking my vertical one and adding 2 vertical ones, taking my vertical one and adding a square, taking my vertical one and adding 2 horizontal ones. So that's how we got there. So you may have to go back in the video, but we did go through the whole examples and derivation of this. Yeah, this recording will be up as soon as we're done. And always, I know there was one time where like Professor Darden forgot to post it as public. The link in the schedule of topics always works. Even later, it'll still link to the right thing. But I try to remember to make them public as soon as lecture ends. Well, there's a step in any DP problem where you have to make that sort of logical step of how do I get from A to B. And so when I looked at this problem, I said, well, I'm not going to, when I try to tile 17, I'm not going to look backwards to 1 and tile the whole thing. Because all of my segments either have a vertical size of 1 or they have a vertical size of 2. So the width is either 1 or the width is 2. So that's all I can add. So that's how I knew I only had to go back to tilings of I-1 or tilings of I-2. That's how I knew that there were only 2 steps backward I had to look, because that's how I would get here. Is I would take something that was 1 smaller and add a vertical 1, or I would take something that was 2 smaller and add one of those things to it. So that's how I knew to limit myself to I-1 and I-2. And then how did I know it was 2 times or 1 time or 3 times? Is I did this example. As I said, hey, if I take this one, I can add 3 different things. But when I start with this, really there's only one thing I can do. So when I look back at the I-1 and I add 1 vertical one, there's only really, I said or here, but there's really only one way to get here. The only way to get here is to add the vertical one. I've got to take what I've got and add the vertical one. So that's how I knew this one was not multiplied by anything, because I could take the size -1 and just add a vertical 1 to it. There was only one way to do that. So it was this number of tilings, and I have to add a vertical 1. Whereas if I went 2 back, I could add one of 1, 2, 3 different things. Now, we could go around and around on this one for 8 hours, and some people still would not necessarily get it. Or someone would join late and we'd start over again. But look back at this one, think about it, go back to the video, and then go do another problem. Because there's another practice exam with another DP problem, and we want you to work on it. We really want you to work on it before you look at the answer. Think about it, because there is practicing these DP problems is going to make you better at them. So we've got this one, we've got another practice exam, 2 combined, and then we've got a bunch of others that are posted on Canvas. Okay, let's move along to the next coding problem here. And this one, oh, I get it. I was right. I did load up the question file. It looks like I goofed on the question file. It looks like the question file, I accidentally put one of the answers in the question file. Because what I did was I added the bottom-up solution recently. And apparently I forgot to protect the bottom-up solution and not put it in the question. So I goofed on that one. I'm going to have to fix that. It's in my LaTeX code. I got an error in my LaTeX code. Okay, so for this one, we didn't put the answer there. That's good. Okay, so we've got to look at each of these questions separately. So this one is basically searching in a tree. This exam was a little bit odd in that it had 3 coding questions, but none of them was huge, and the second 2 were related. That's unusual. Your exam has 2 completely unrelated problems. Okay, so we said here we've got a set that can efficiently see if it contains a given element. And so let's say we took a node with a pointer to left and right, and we could make a BST from that. And if we make a BST from it, then we could have average case log n lookup to see if something exists in the set. Now, if it was an AVL tree, it would be guaranteed log of n. And since you don't have to write the insert, since you just have to write exists, I suppose we could have made this problem an AVL tree, and then it would be not just average case, it would be big O of log n. And I say big O of log n because it's best or worst. Like best case, you can always find it at the root. That's why this says big O, because we could always get lucky and find it at the root. It could be O of 1, but on average, it's going to be log n. And if it was an AVL, it would be worst case log of n, and average case log n, but best would still be O of 1. Now, this one is a little bit unusual. It says, you may use up to log n auxiliary space. That was in case someone wrote a recursive solution and it wasn't tail recursive, they still wouldn't lose points. So this one, we can write it iteratively, we can write it recursively, and my recursive solution is probably going to end up being tail recursive. But just in case, we wanted to give you the upper limit there. Now, let me look. Okay, it's not here. Let me look on my PC. Okay, yeah, so this one, the PC does have both solutions. The recursive solution and the iterative solution will auto-reveal at 130. Okay, so we can write either one together. They're both in the PDF when the answers reveal. Let's do the recursive solution together, because I think my intuition is that students are not as comfortable with recursion as I am after more years of coding. So let's look at the recursive solution. All right, well, if we're doing a recursive solution, I need a base case, right? If the node pointer that you gave me is equal to null pointer. So if I reach a null pointer, so I'm looking for like 5 in the set of integers. I'm looking for 5, and I look left, I looked right, I looked left, I looked left, and I find a null pointer, then I can say, oh, return false. It's not in here. We could also write this as if not node would be equivalent. Write it whichever way makes sense to you. Okay, so that would be a base case. We've reached a null pointer, we never found it. Okay, what about if it isn't a null pointer? We could look for, we could look left, we could look right, or we could look at the value, we could look to see if we actually found it. I think most people are probably going to do the equivalency first. All right, so if node arrow, what's it called in the structure? Val is equal to the parameter that was passed in, val, okay, then we can return true. Spencer, get off the table. You're not allowed up there. Okay, so that takes care of if we found it. Now we need an if for should we look to the left or the right. I tend to, in this case, I tend to do left first. So if the node value is greater than what I'm looking for, so I'm seeing like a 10 and I'm looking for 5, then I know I should look to the left. So then I should return the recursive call, which is exists. And I've got to give it a node pointer, so that would be node arrow left, comma, we got to give it the value again. So there's our recursive call. And then we could do an else here, or we could just write the return statement. It doesn't really matter. Let's save a line of code and just say return recursive call of exists of node arrow right, comma val. So we'll make the recursive call and we'll give back whatever we found from the recursive call. And since we do have two recursive paths, our recursive paths, they do the node follow the pointer arrow first before the call. So when the recursive call is done, it can immediately return. So these are both tail recursive. So we didn't really need the log n auxiliary space for the stack because we've got a tail recursive solution. And like I said, I think most people's coding of this would end up being tail recursive, but if it wasn't, then you'd have room for that stack space. What is it about the... Oh, yeah, it's just in general. This one, we just said use whatever you want. We didn't think people would use anything. I think this semester we're being more specific. So there's nothing you really need from the STL to solve this problem. Okay, and I need a curly brace for the end of my function. Okay, so that's our exists. That was number 26 for this exam. All right, so let's look at, there's a blank page for drawing, and then get off the table, doofus. Okay, so then this one is searching in a hash table. So this is actually similar to Lab 7, except requirements, your solution must implement quadratic probing. So we just have to do an exists, and one thing we did, which I gave you the real exam question from the previous semester. The thing that we did here was, rather than giving you a class and saying you are writing a member function, we just gave you a struct, basically. The hash table is in a structure, and you have to implement exists as a standalone function. Now, one thing that causes you to do is you're going to be saying in the code a lot, you're going to be saying like TBL. You're going to have to say TBL dot buckets dot size. So you're going to have to find yourself saying TBL dot a couple times. So we thought this one would be easier to write up and easier to understand if it wasn't a member function where we had to describe the member variables and stuff like that. So we made it, it's very similar to Lab 7, but we made it basically a standalone function instead of a class. Okay, your hair's getting pushed in since you can't stay off the table. All right, sorry about that, cat interruptions. Okay, so we've got to write the code for this one. So we've got to do quadratic probing. Now, one thing we want to do is we want to prevent ourselves from looping forever. So if we keep finding, Spencer, get off the table, you naughty butt. Okay, so one thing we want to do is we want to make sure we don't loop forever. And there's a couple different ways to do this. I'm going to do something different from the solution that's in the PDF because we've got that luxury. We can write the code differently. So in the solution in the PDF, I thought of it as a do-while loop. But this time, let's write it as a for loop. I think that's what most students, the way most students think of it, as a for loop. I thought of it as a do-while loop because I knew I would have to probe at least once. Even if I get lucky and it's right where it should be, where the hash function says it should be, then I'm okay there. Okay, and the other thing it says for the hashing is, somewhere in here it says, just val modulo m. So the hash function, we didn't have to worry about creating an object of a hasher class or anything like that. Whatever value you're given, you can just use that value modulo m. But be careful in your code. There's nothing m passed into you. When we say m, we mean table.buckets.size. Okay, so we're going to have an index of where we're going to start. And we're actually going to have to keep that starting index to do quadratic probing properly. Because remember, quadratic probing says we do the hash, and then if it's not there, we skip forward from the original position 1 squared or 2 squared or 3 squared or 4 squared. It's not 1 squared from the previous one, 2 squared from there, 3 squared from there. It's always original location plus j squared. All right, so I'm going to make, before we start a loop, I'm going to need some variables for like, what is my starting index and well, actually current index we can do inside the loop. We can do that. Okay, so I'm going to need a start index. And I'm going to do it as a size t because that's what's easy for an index. Really, we could do size t here. We could do int here. It doesn't much matter. Let's just do int. Let's be totally different from the PDF. Okay, so let's do int start index is equal to, well, that would be my val modulo tbl dot buckets dot size. Now you could, if you were writing this by hand, you could save yourself some time by just making a variable and setting it equal to table.buckets.size. You could say like int m equals table.buckets.size, and then we could save some writing by hand later on. When you're typing, not a big deal either way. Okay, so that's my starting index, so then we can go into the for loop. For int j is equal to 0. J is, remember, that's in the formula. That's the count of how many times we've probed. Okay, so j equals 0. J is less than table.buckets.size because I'm not going to loop forever. If I keep finding deleted over and over and over again, I don't want to loop forever. And then plus j. Okay, so there's my for loop. So now what I've got to do is figure out my current index. So my index is equal to, well, that would be my start index plus j times j modulo tbl dot buckets dot size. Hopefully that's the last time we're going to have to write that. Okay, so we take the start index, we add j squared, which initially is 0, so that's just start index, modulo table.buckets.size. I suppose now that I look at the code, I could have left out that modulo because it's going to get moduloed later. Oh well, hindsight is great. Okay, so that's my index. So that's where I want to look right now. So we've got to check a couple things. We've got to check if it's occupied and the right value. We've got to check if it's empty. We can do them in either order. It doesn't matter. Let's do it in what I expect students like to do first. They want to know if they found it. Okay, so if they want to know if they found it, we can do an if. If this would be tbl dot status at this index is equal. This would be looking for occupied status colon occupied. Okay, so if that's true, oh, whoops, nope, closing parenthesis, we're not done yet. And tbl.buckets subindex is equal the val I'm looking for. So if it's occupied and it's the value I'm looking for, I've got a typo here. think so. No. Okay, yeah, I've got a vector of buckets. Oh, remember, and then a bucket is, oh, I got it. This is vector events. Okay, yeah, this is fine. Okay. So yeah, I don't have anything else in there. Yep, that's right. So if that's true, so if we've got occupied and the value is right, we can return true. Okay, so that's if it's occupied in the right value. Now, if I find an empty one that's never had anything in it, I can return false. So I can do that here if tbl.status subindex is equal status colon what is it called, empty? Yep, empty. So if I find an empty one, I can immediately return false. And if it's deleted, we just keep the loop going. So that's basically the end of my for loop. Okay, so that's the end of my for loop. Now, if we looped enough where the for loop just ended without ever hitting any of the other returns, we've got to do a return false, because there's nothing there. We never found it. We found a bunch of deleted ones over and over, or we found occupied ones with wrong values, or we found deleted ones. Whatever it is, that's the end of the function. So we've got to return false to say we never found it. So this one should just keep looping around until it either finds it, finds an empty one, which means we can stop, or the loop just has to stop. You do have to check if it's occupied. What if I put a 5 in there and then I deleted it and then I say, is 5 in there? So there's basically, in any solution like this, there's rubric items for doing things right, basically. So there's a rubric item basically like, did you properly check if it was, what you were looking for? So you might, if you didn't do the occupied, if you just check the value, you might lose a couple points. And if you leave off the check for empty, you'd lose a couple points. And if you don't do the modulus right, you'd lose a couple points. So there's all kinds of things that you can do right, and you can do them partially right and still get points. So if you miss the return false at the end, you'd lose a point or two. You'll get most of them. But every little thing that you want could lose, every little thing that you do wrong can lose points. That's the solution that's on the PDF, is a do while loop that stops if I get back to the starting point. So basically, the solution that we did today says you're going to loop n times at most. The one that's in the PDF that'll auto reveal at 130 does a do while loop to say, start here, and if you ever get back to that starting index, you're done. You've looked everywhere you're going to possibly find. So yeah, it's written the opposite way in the PDF. Okay. Well, we try not to double count. So someone said, what if you leave off the second one and it loops forever? Well, it won't loop forever, because the for loop, if the for loop is going to limit it to n time. So without the second if, you wouldn't lose the complexity points because the for loop stops it. But if your for loop loops forever and you don't check, then you could lose points for both. You could lose complexity points and you could lose points for the missing comparison. But we try not to double penalize you for the same thing. So if something causes you to do two things wrong, we try not to double penalize you for it. And we try to be, that's one of the hard parts about grading these, is making sure we don't double penalize students when we shouldn't. Okay, if you've got more questions on these, also feel free to come to office hours, proffice hours with questions. We'll be happy to answer them. Hello, buddy. Okay, so let's go back to the PDF that we've got ready, the review slides, and we'll do some more in here. Okay, so we talked about topics. So trees. So we talked about trees in general, binary trees where we're limited to the number of children of each node is 2, binary search trees where we put a rule about look left for small values, look right for bigger values, and then AVL trees which are forced to be balanced at all times. Now we gave an example here which we can do a little bit of it together. So it says we've got a bunch of values that we want to insert. 4, 2, 3, 5, 7. Okay, I'm just going to remember that. 4, 3, 5, 7. Okay, so I've got a blank slide here, so we want to do 4, 2, 3, 5, 7. All right, so let's do a few inserts together. So I start with an empty tree. Well, I insert 4, that becomes the root. And then if I insert the 2, that would have to go to the left of 4. Then if I insert 3, then we've got to, oh, I see there's more questions, and apparently my bat signal had 0 effect. So it says for a DP problem, do we get the majority of the points on getting the recursive relation right? Well, we try not to make the most points from the hardest part. We try to make the rubric so that you can get some points for having a memo that's the right size, returning something from the memo. Even if it's the wrong value, you return something from the memo. You've got some looping that's going to try to loop over the right number of things. You've got a relationship, even if it's not the right relationship. So everything that you can put in there is going to get you some points. Even if it's not right, it may get some points just for being present. Like you have a relationship, might be 2 points, and the right relationship might be another 2, just for example. I don't know what our rubric is going to be. We haven't created it yet. But everything that you do right can get you points. And so, I mean, what I'm saying is don't throw in code. We can tell the difference between I threw some garbage in here just so there was garbage and I actually made an attempt. So, but if there's a memo and you try to use it and you try to loop and you try to return something, even if there's things wrong, those things can get you points. But at least be on the way to a solution. Things that you will get points for things that need to be in a solution. You won't get points for code that just happens to be code. But if it's code that is halfway on the right track to a solution, you can get points from that. Okay, so for this one, 4, 2. Okay, then when I insert 3, I'm unbalanced. And if we look at the balance factor of every node, remember the balance factor is left height minus right height. So a leaf has a balance factor of 0. 2 has height of 0 minus 1 is -1. 4 has 2 minus 0 is +2. So this one is out of balance, and when we see a +2, we look left. And if we see a negative there, we need to do a double rotation. So this tells me I need to do a double rotation. I'm going to write that down so I don't forget. So the first thing I've got to do is I've got to do a rotate left at 2. So rotate left at 2 produces 4, 3, 2, and the double rotation there reminds me I'm not done yet. I've got to do a rotate right at 4. Whoops, that's not very well written. So I've got to do a rotate right at 4, gives me 3, 2, 4. Okay, from there, this tree is perfectly balanced. I know I can insert one thing without having any problems. 2 might cause it to be unbalanced, but I can at least insert one more. So I insert 5, and it's still balanced. I insert 7's got to be to the left of, or to the right of 5. And now we're unbalanced. And if we look at our balance factors, we've got 0, 0 minus 1 is negative 1, 0 minus 2 is negative 2. I've got a negative 2. When I've got a negative 2, I look to the right and I see that's a negative number. So that's fine. I've got a negative 2 with a negative 1 to the right of it. That's just a single rotation. So I just have to rotate left at 4, which would give me, so the 3 and the 2 don't change, and then 4 and 5 change their relationship. 5 moves up, 4 moves down, 7 just moves along with the 5. All right, so there's our rotate left at 4. And then what was the next one? We could insert 7, 8, 9. So if we inserted, let's do one more insert. I'll change colors again here. If we were to insert 8, that would have to go, we're running out of room, that would have to go to the right of 7. And now let's look at our balance factors. We've got 8 has a balance factor of 0, it's a leaf. 7 is 0 minus 1 is negative 1. 5 is 1 minus 2 is negative 1. 3's balance factor is 1 minus 3 is negative 2. So node 3 is out of balance. We look to the, because it's a negative, we look to the right of it. Right of it, I see a negative 1, so I know I just need a single rotation. I've got to rotate left at 3. So 5 moves up, 3 moves down to become its child, 2 moves along with 3, 7 moves along with 5, and then 4 has to get displaced. 5 got a new left child, 3 lost its right child, 3 has room for a new right child, and so 4 would have to go there. Now 4 has to go there to make, oops, I forgot to bring 8 along for the ride. 8 goes with 7. 4 has to go to the right of 3 because it's a binary search tree. If the values are all unique, it's easy to see where that 4 should go. It's if there's duplicate values that you've got to be careful and look at who changed their relationship. So whoever became a parent and lost a child, then whoever changed from being a parent to being a child has a new open child relationship. So when two things change roles, the new parent takes on the old parent as its child, but then the old parent has room for a child where it lost the one that became its parent. So you can do it by unique values if they're all unique, or look at who lost a child, they have room to gain a child if there's duplicates. And then you could continue on from there. We could insert 9, etc. 9 will produce a rotation, and then we can do, so 9 would produce a rotation, and we'd end up with a perfectly balanced tree, and then we could do 2 more insertions, etc. So do that for practice. Okay, hashing. So hashing functions, hash tables. We talked about separate chaining, linear probing, quadratic probing, double hashing. Remember, we also we talked about dynamic hashing, which in Lab 7, that was your rehash and grow function. No matter what collision resolution scheme we use, we might have to grow the hash table at some point. And if we grow the hash table, we have to take everyone out of the old table and insert them into the new one because they could change their index. Imagine if I had a thing, I did the hash function, like I've got key 1, I do h of key 1, right, is equal to the translation of key 1 modulo m, okay, and h of key 2 is equal to the translation of key 2 modulo m. Now let's say that both the translation of key 1 and key 2 went to similar places. Let's say this one translated to 6, this one translated to 2, but my m was 4. I had a table of size 4. That means that they would both want to go to index 2. And depending on the resolution scheme, the second one would get bumped either to the next location or added to a chain, etc. But if I grow the hash table, let's say I do something after this and I go, oh, wait, I want to add a new one, but I'm already half full. Let's grow it before I add a third one. 50% I was okay with, but 3/4 I'm not. So before we add that third one, I've got to grow this table. So I grow it out to size 8 instead of 4. And now what used to be, both of them used to be at index 2. Either they got chained in a separate chaining or they got bumped to 2 and then 3. Now in a bigger table though, key 1 goes at index 2 and key 2 goes at index 6. Oh, whoops, I got it backwards. Key 2, key 1. So key 1 goes to 6, key 2 goes to index 2, because now when I'm doing modulo 8, we get new indices. So that's why when you grow, you've got to take everything out of the old one that's occupied and rehash it into the new one to decide where it goes. Mind reviewing separate chain? No, not at all. So in separate chaining, let's just do an example. I'll just get rid of this table here. So in separate chaining, let's say we start out, like I said, with a size of 4. Basically, my 4 things, 0, 1, 2, 3, would be linked lists. So I'd say, okay, key 1 should go to 6 modulo 4 is 2. So I add a node out here containing key 1, and maybe its value goes with it, depending on whether it's a map or a set. So we'd put key 1 at index 2, and then when I add key 2, well, it depends on how I add it. Let's assume we don't want duplicates. So if I don't want duplicates, well, it doesn't matter. Key 1 and key 2 are different keys anyway. So then I could either end up with key 1 points to key 2, or I might end up with this points to key 2, which points to key 1. The order of the linked list doesn't matter. They just both have to be in there. But when we rehash and grow, if we had deleted elements, we don't want to carry them over. But personally, I wouldn't count deleted elements towards my rehash and grow. I would say, hey, I'm half full. That's still good. Even though everything is deleted, I don't have to grow because everything's empty. If everything's deleted, that means everything's empty, basically. It just might take me a little bit longer to find it. But as soon as I rehash and grow, all the deleted go away. So no matter what I have, however many I deleted I have, the first time I actually grow, the deleted all disappear. But it's not fixed that you have to do it that way. If we want you to do it a certain way, we'll tell you on the exam. Like if we want you to consider deleted towards the load factor, we would say that. Okay, now we've got some slides here with a few questions. There's one of these that's not the best question, and that's why I put it in the review, because it's more of a thinking question than I want you to solve this during the exam sort of question. So it says here, what is our average, what's our complexity for inserting into M slots, a hash table with M slots that stores N unique keys, so we did list that, and we want for separate chaining, we want the best, worst, and average, and then for linear probing, we want the best, worst, and average. Now this one is the hard one. This one you really need to go back to the slides, and I wouldn't put this one on the exam, because we told you when we did the lecture on hashing that we didn't want to do that one. So let's do the 5 that we can do. So for the separate chaining, well let's just do best for both of them. Best case is always O of 1. We can always get O of 1 behavior. We can always get lucky. We hash and it's right where we expect it to be. So or insert, I should say. When we're doing insert, I hash and I find an empty bucket right where I want to insert, and so I can insert right there. So I can always get lucky and find an empty bucket right where I want one. So the best case is O of 1. Then the worst case would be, well, whether it's separate chaining. So separate chaining, what would the worst case look like? Everybody hashes to the same one. And if everybody hashes to the same bucket, then even though the hash table is half full or even a quarter full, if everybody's in the same chain, I can get O of n. Because they're all, just these keys, I got either a bad hash function or keys that just happen to all hash to the same place. I've got the worst possible situation. Everybody goes to index 2, and I get a big chain there. And so when I'm trying to keep them unique, I've got to look at all of them to say, hey, I can't put 5 in here if there's already a 5 in this linked list. I have to look through the whole linked list. For linear probing, now even if we say my hash table is not going to get more than half full, but there's still n things in there, those n things in linear probing could be one big cluster. They could all be in a row, and then I go to insert a new one, and I have to look at all, and my hash, and it says right here, the first occupied one, occupied, 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 occupied. It's one big cluster, could be O of n. All right, so the best and the worst, pretty easy, because those should just be true for any, even if we're doing, whether we're doing quadratic probing or double hashing, we would still get the same thing, same best, same worst. All hash tables have the same best and same worst. The average is what's different. So for a linked list with a separate chaining, the average, AVG, the average should be O of n over m, which is equal to O of alpha, which we'd like to have approximately equal to O of 1, assuming that we don't just keep the table size the same, assuming we grow it at some point. You know, we pick a load factor. Well, that load factor is the length of the average chain. So some of them might be longer, some will be shorter, but on average, the average chain will be of size n divided by m. I've got n distinct keys spread across m buckets. That's the average. Now for the linear probing average, go back and look at the slides. There's a big complicated formula in there that you don't need to know for the exam. We're not going to ask you that one for the exam. But if you want to be complete, go look at it. But it's not going to be on the exam. And then if we did search, search is the same complexity as insert. If we did remove, remove is the same complexity as insert because we've got to go do all the same things. We've got to look in all the same places. Okay, graphs. So graphs in general, we've got a bunch of terminology, which I repeated on the next slide. And then we've got a bunch of terminology. Adjacency matrix was when we had a dense graph, adjacency list, when we have a sparse graph. We talked about depth first search and breadth first search. We talked about Prim's algorithm and Kruskal's algorithm for solving MSTs. We talked about Dijkstra for shortest path. Remember, Floyd-Warshall is in the slides. I put it in here to remind you to cross it out. It's in the slides because there was one semester where we had room for it, but we haven't done it since. So we've made sure there are no Floyd-Warshall questions on the exam. So the graph terminology, edges, vertices, and nodes, and I tend to, out loud and in the problems, we might use vertex and node in different problems. One problem might say vertices, another one might say nodes. So just get used to those. Degree is actually something I should get rid of our terminology. Degree we didn't talk about, forget that one. Weight of an edge, weight, cost, etc., the number associated with an edge. Like, you know, this edge is a cost 87 or 42.3. You could be a Euclidean distance, etc. We could have directed or undirected graphs. We could have, if we don't say otherwise, unless we say that there are allowed to be loops or loops meaning self loops, like a node connects to itself, or parallel edges. If we don't say that's allowed, you can assume it's not allowed. So unless we say otherwise, you can assume it's a simple graph. There's no self loops. There's no parallel edges. There's never two ways to get from A to B directly. And there's never a way to get from A to A directly. Indirectly, well, that could happen. It's a graph. The adjacency matrix and adjacency list, you can review those. And then sparse, we said basically we could say two definitions of sparse. We said here E is much less than V squared, or whoops, just one vertical bar there. We could also say that E is approximately a constant times the size of V. So it's proportional to a constant times V, not V times V. So either one of those definitions works to get the idea of sparse across. It's either much less than V squared or it's approximately equal to a constant times V. Whereas a dense graph, the number of edges is proportional to V squared. And like I said, when I talk to students in the office hours about the Project 4, Part A, if half of them are in the medical and half of them are in the normal campus, then we get n over 2 times n over 2 minus 1 over 2 in each half. That's n squared over 8 plus n squared over 8 is approximately equal to n squared over 4. That's still a dense graph. N squared over 4 is just half of n squared over 2. So even if half of them are medical, half are normal, and well, we got to have at least one border, it's still a dense graph because it's much closer to V squared than it is to V. So there is no strict definition of here is the line between dense and sparse. But in general, we're not going to ask you, we're not going to give you a graph with like 100 nodes and X number of edges and ask you to categorize it. But we just want you to understand the dense ones happen to be proportional to V squared, the sparse ones are more proportional to V. But there is no one place to draw the line between them. But when you know a graph is dense or sparse, tells you what algorithms to use on it. One second. So we talked about a simple path. A simple path is a path where nothing is repeated. Connected graph is a graph where there is a simple path between every possible pair of nodes. You can somehow get there from here. In a cycle is basically a cycle is a simple path where the first and last nodes are the same. We talked mostly about an MST, a minimum spanning tree. A minimum spanning tree is just a spanning tree with a minimum weight. So if I had a graph, like, let me just erase the markings on here. If I had a graph like this, then that is a spanning tree. It connects all of the nodes while creating a tree, but it's not minimum, probably. Probably a minimum tree would look more like that. So we could have a spanning tree that's not minimum, but generally, when we have a spanning tree, we want to get the minimum weight. And we talked about the Hamiltonian cycles with respect to the traveling salesperson problem. So a Hamiltonian cycle is a cycle that hits every node exactly once, except for the beginning and end are the same, since it's a cycle. And we looked at a bunch of different graph problems. The one you know the best, the one that we did the most work on with the project is, of course, the traveling salesperson. But we also looked at the graph coloring, we looked at knapsack, we looked at the n queens problem. looked at all those as different types of graph traversal problems. Now we've got on the next slide, I think, yep. On the next slide, we've got a graph and it says, do prims and Kruskals on this graph. Now the start at A, that would go with prims. That would be the one with a distance of 0. Now I hope, after doing project 4 part A, you've had enough prims that you know how to do it now. So let's take a few minutes and do this one together with Kruskal. Now, if we're going to do Kruskal, remember the first thing we have to do is we have to sort all of the edges into ascending order. I don't feel like writing them all down like CF is 1, CD is 2, FG is 2, etc. I'm not going to do that. I'm just going to do it without listing them all in order. We're just going to have to be careful. All right, so edges of length 1. So we know if we're doing Kruskal, what do we know? We know it's got no negative edge weights. All right, well, or no, sorry. We don't know that for Kruskal, do we? Yes, I think we know that. So we can start at the lowest weight is 1. So we start at 1. I'm going to keep this edge. So I've got that edge from C and D, and so now C and D are both in, basically. All right, then I've got edges of length 2. I could pick them in any order. Even if I end up being able to pick only one or the other, I would end up with equivalent MSTs. So let's go alphabetically. First would be CD. We take the CD of weight 2, and we've got that one's connected. FG of length 2, we can pick that one without producing a cycle. See, with the first two edges, I didn't have to check for cycles. Now I have to start looking to make sure I don't produce a cycle. So I can take the edge from F to G at length 2, and now we could use edges of length 3. I don't see any edges of length 3. Okay, edges of length 4. I see 1. So we can take the edge of length 4. And now A and B are connected. And they're connected in basically a different subtree. C, D, F, and G are all connected together into a tree. A and B are connected into a different tree. Okay, so that's the only edge of length 4. Edges of length 5. 2, 5, 6, 7. Okay, so I see one edge of length 5 from E to F. So we're going to have to take that edge from E to F. And now E is been visited. It's in there. And really, we don't really have an idea of in and out in Kruskal. We would really be doing union find behind the scenes. Now you should know union find because we covered it in these slides, but you don't need to do union find just to solve this. So we got 5. How about edges of length 6? Are there any edges of length 6? Yeah, I see 1 from E to G. But if I include the edge from E to G, I get a cycle, so I can't take that one. Oh, I should have been circling these. The 2 is in, the 2 is in, the 4 is in, the 5 is in, 6 is out. Okay, I think I'm caught up. Okay, so the 6 is out. 7. I see one edge of length 7, but if we take the edge of length 7, we produce a cycle, so we don't want that one. Edges of length 8. I see 1, 2 of them. All right, 1, 2 of them. We've got to do them in some order. Let's try alphabetically. First would be AC. So we try the edge AC. Does AC produce a cycle? No, it doesn't. So we can take the edge from A to C. And now those two, what used to be 2 separate subtrees, are now connected into 1. Now, if we were keeping track, we would see we're down to 1 tree and everything's in it. But another way we could do is we could just look at all the edges. Let's just check all the edges, and if they produce a cycle, we don't include them. Does the other 8 produce a cycle? Yes, it does. We can't pick the other 8. There's 2 9s, B, C, and D, F. We'll do the BC first. That 9 produces a cycle. The other 9 produces a cycle. The edge of length 10 produces a cycle. And so we're done. So we've picked the edges. So what's our weight? 4 and 8 is 12, 14, 15, 16, 17, and 5, it looks like a weight of 22. And then on the next slide on mine, I've got the which ones we picked mapped out. So we have a 22 either way. We could pick that 8 or we could pick that one. We can't pick both. But either way, we'd have the same cost. We'd still have a cost of 22 no matter which one we take, but we would have different edges in each one of them. Okay, how are we doing on time? We're out of time here. Okay, Prim's algorithm, we've run through a lot. Kruskal's algorithm, we pre-sort the edges, try to insert them, and do union find to make sure that we don't duplicate things. Dijkstra's is almost identical to Prim's, except it's a cumulative weight to reach a new edge. It's the weight to get to the current vertex plus the new edge is the total weight to visit that one. So Prim's and Dijkstra's are almost the same, except Dijkstra uses a cumulative weight. And then this is mostly review, shortest paths. So do Dijkstra's on this one. So if we start at A has a distance of 0. And then what can we pick? Well, if we've got to go from A to somewhere, the only false ones we can reach are B or C. We'd pick B. So now B has a distance of 4. Then what can I reach? C at 8, C at 13, E at 14, D at 12. Looks like C at a distance of 8. And now I could go to E at 14, D at 12, D at 10, F at 9. Sounds like F is going to be next. Okay, so you can do Dijkstra's without a table. You just got to be really careful. So we end up with that graph. I just want to get a few of these things in the video before we end, and I know we're over a few minutes. Algorithm families, we talked about those. Go back through the list. Brute force is just a simple, not always simple, but a straightforward way to solve it that's usually inefficient. Greedy, we make the best decision we can, and we never reconsider it. Greedy is sometimes optimal, sometimes it's not. For some problems, it's always optimal. So Prim's algorithm, Kruskal's algorithm, Dijkstra's algorithm are all greedy, and as long as you follow their rules of about what's allowed, then you get an optimal solution. But some, like knapsack, greedy is not usually optimal. For a specific set of data, it might be. But for fractional greedy, it's always optimal because of the fractional. Divide and conquer, we talked about when we have non-overlapping subproblems. Dynamic programming, when we have overlapping subproblems. Backtracking and branch and bound, when we don't have a better approach. When greedy doesn't work, when DP doesn't work, then we can rely on these to be no worse than brute force and usually better than brute force due to pruning. Now we've got a question here. So there's this version of Fibonacci. We want to know, what is it? What family would we describe this as? So this one says solve both subproblems. So this one, and it also says write 2 versions of it. And I want to get these in the video so that people can look at them later. So I would call this brute force. You can't call it divide and conquer because the subproblems overlap. It's not greedy. You're not picking the best one first and not changing your mind. It's not DP because it doesn't have a memo. So here's one version of Fibonacci using a static unordered map. So we use one unordered map, and then we don't have to figure out, like we did in the slides, we had a solution that had a memo, and we figured out like what's the biggest integer we can put in there. Here we just said, hey, use an unsigned key and a uint64t value. So n is the key, Fibonacci of n is the value, and if you change the type, if a uint128t becomes available, change this and it'll either work or it'll fail. If you ask for too big of a Fibonacci, like with this one as is, if you ask for fib of 100, you'll get a wrong answer because fib of 100 won't fit in a uint 64. So there's a top-down solution with a static hash table. Here's a bottom-up solution that just keeps a couple variables. It doesn't have a full-on memo. It just keeps basically the previous two. And then it figures out a new one based on the previous two. And then last couple slides here. Hopefully you've got a feeling of accomplishment, having come through 281, going from, what do you mean we don't get starter files and we have to write it ourselves, to project 2, wait a minute, you gave us templated files, that wasn't what we wanted, to project 3, project 4. Project 4, you're writing your own project, you're investigating heuristics, implementing heuristics based on what you've read about them, getting them to work. And so hopefully you appreciate how far you've come in this class and the feeling of accomplishment from a lot of things learned. And so next things, basically prereq for a lot of upper level courses. I think EECS 440 is usually winter, and there is not 381 anymore. Did I remember to take it out of the list? Yeah, so I took 381 out of the list because David Kruskal retired. We voted unanimously that he wasn't allowed to retire. He ignored us. It was a joke vote. So 381, there's no one teaching 381, although 440 covers some of the same things, some of them, not all of them, but some of the things that 381 covered. And Nicole Hamilton, who teaches it, was at Microsoft when Bing was started. So thank you, everyone, for a successful semester, and we'll see you on Friday, or we'll see you in office hours before that, and good luck on the exam.